So today we are going to start with this classification problem now. So can you see the slide? Hello.
Yes, ma'am.
Okay, so we will be starting with the classification problem. So all of you know classification problem um, is a problem given this data set where you again have set of kind of predictors x's and you have a output variable. So this output variable is typically a set of possible classes. So it's a categorical value. So in classification problem, what we try to identify, so we are talking about the supervised classification algorithm, meaning that so the data is labeled in the sense that for a set of features x, there is a class defined for that particular feature for every entry, and so it is called a labeled data set. And given a new x value, we would like to um, predict what is the class of that given entry x. So this is a super. So earlier when we studied about regression, so regression is also supervised, right? Because again, for a set of x features, the output variable y or the dependent variable y um, is given, and given a new x value, we are supposed to predict what is the value of y. But there, this y values are were always generally it is real values. So the question came up that whether we can apply. So that's the question. First, we will just see regression and classification, how they relate or how they don't relate. So in regression, we saw that so in regression, we were estimating the function f of x given p predictors, this x1, x2, xp, and the response y. So it is supervised. That's why we say it is regression is also supervised. The relationship was given by this y equal to f of x plus this epsilon. So we either predict this y cap using parametric or non-parametric methods, and we also we can infer, that is the relationship between the predictors and response variable. So we talk about lots of inferences, the different ways of using inferring the relationship between the predictors and the um, response, using that p value, the t statistics, and things like that. Then different measuring parameters in order to identify what kind of relationship there is among the different predictor variables and the response variables. So that's why it is written either we predict or infer. Use less flexible models for inference and more flexible models for accurate predictions. So we have only seen regression over here, but the flexible models would mean that either linear regression, you make it to be multiple linear regression, or you make it polynomial regression and things like that, or you can go for more machine learning like algorithms like neural networks and things like that. So now, how let's now do a kind of comparison kind of things with the regression and the classification problem. So as I said, in case of regression, so response or I mean in general, this response variable y may be either quantitative, numerical, or it may be qualitative, that is categorical. So that is values in one of the k classes. So typically problems with a quantitative response are considered regression problems, and while those involving a qualitative response, meaning these categorical values or classes, are typically termed as classification problems. But obviously this distinction is not always very clear. So there are like regression, there are different ways of doing this classification algorithm. So one thing possible is that maybe the question is whether can we apply the regression line to find what is a class. Yes, of course we can do that. We can use the regression line to find what is the class, but the problem is that the response y is going to be mostly real values, and mapping those real values to a class value, which are generally distinct integer values. Typically classes are represented by some in case of binary classes, two classes will be having 0 or 1, or if you have multiple classes it will be represented by distinct integer values. So if you apply regression in order to do a classification, the logic remains the same, but the problem is how do you map the predicted y value to one of these classes. So that actually makes linear regression not suitable for doing the classification. Still, you can do some kind of approximation in order to map those real values to a classes by setting some range or something like that for binary class or multi-class. But still, there will be the errors will be quite a lot, and you cannot do any kind of inference, or you cannot guarantee the kind of errors that you will be getting. So least square linear regression is used with a quantitative response. In order to cater to these categorical values, there is what is called logistic regression. So we will study logistic regression in the next class. So this logistic regression is actually used with a qualitative response. So maybe two class binary, and or it can be used as a multi-class also, but in a different fashion. But typically we will be talking about this binary logistic regression, so often used as a classification method. And what happens in this logistic regression is that it estimates essentially the class probabilities. So what is the probability that a particular entry will belong to a particular class? Okay, so that's why we can say that it can be thought of like a regression method as well. So logistic regression, that's why it is called logistic regression. Okay, so it tries to optimize, just like in linear regression we were minimizing the least square, we are minimizing the error, and from there we got the formula for finding out the parameters of linear regression. In logistic regression also we try to minimize certain parameters, and we try to minimize the error using the probabilities, and finally what we get is out of this logistic regression is that it gives a probability of a particular entry being belonging to a particular class. So that's why this is also called a regression. So it minimizes certain kind of errors in this. Okay. So some statistical methods. So you have possibly studied k-nearest neighbor and boosting algorithms. So typical classification methods can be used for either quantitative or qualitative responses. So this k-nearest neighbor, even though we know it only for classification purposes, but yes, with some kind of modifications, we can use them for doing the regression also. It can be done to get the quantitative response also. So the numerical response also we can get using this k-nearest neighbor or boosting algorithms, the algorithms which are typically used for classification. So, however, whether the predictors are qualitative or quantitative is generally considered less important. So with all these things, what I'm trying to mean is that this regression, linear regression, logistic regression, or methods like statistical methods like k nearest neighbor or boosting algorithms, like they can be used for both the purposes, like prediction of real values or prediction of a k classes, as in classification problem. But the amount of error that is going to be uh, differing, and one method may not be suitable for other. For example, numerical, when you are doing classification, probably using the regression methods will not be very useful, although theoretically it is possible to apply them. Okay, so the next comes, so supervised and versus unsupervised learning. So all of you know what it is. So, so simple linear regression model, as I said, it is supervised learning because response Y is predicted or inferred using the simple linear regression model built on the predictor and the response measurements. And logistic regression, support vector machine. So these two things we will be learning in this class, logistic regression and support vector machines, probably in the next class. These are also the examples of supervised learning. And so when you talk about classification, we also talk about unsupervised learning. So unsupervised learning means where data is not labeled, in the sense that there is no predicted class, there is no class identification given in the data. So what we need to do is we want to find kind of natural similarities in the data sets. So how do you find these natural similarities in the data sets? There are certain methods. So typically the algorithms that are used for this unsupervised learning is called clustering or cluster analysis. So in unsupervised learning, it describes situation in which for every observation I, 1 to n, there is a vector of measurements xi, but no associated response yi. So that's why it is not labeled, and that's why it is called unsupervised. There is no one to supervise what class that data is going to belong to. And that's why it is not possible to fit a linear regression or logistic regression model, because there is no response variable, which is required for linear regression or logistic regression. So typically we try to identify, as I said, the natural cluster or natural similarities of natural groups present in the data. So these are called clustering method. So the goal of cluster analysis or clustering is to ascertain on the basis of this set of features whether the observation fall into relatively distinct groups. Okay, so that is what I was talking about, the natural cluster or natural grouping. So with this basic assumption, now first, before going into the classification algorithm, in the beginning, first we will see how to assess the model accuracy for classification problems. And from there, how the theory has developed. Even though today we are not going to do the logistic regression, but still this will be helpful for that part also. So whatever model you define, we need to assess the model accuracy. So how you do it for the classification problem. So typically what we define is what is called the error rate for classification problems. Okay, so when we are so these error rate things, we are, so you know that typically classification problems, what you find is those confusion matrix, then accuracy, precision, recall, and those kind of things. You divide into test set and training set, and then you apply some model on the training set, and then you apply your test data, and then find that confusion matrix, and from there you find the accuracy and things like that. But when we are trying to, just like linear regression, where we are minimizing the error by certain means, so there was a theoretical background to it. So we could infer, and we could say what is the, with what kind of confidence our parameters are correct. So similar to that, even for classification, some statistical methods which are theoretically proven can be constructed. Okay, and that is why this error rate is defined to assess the accuracy of the algorithm. Okay, and that's why we are studying this error rate. So um, for logistic regressions, and even for this naive based classification. Okay, so these type of problems we can utilize, or I mean utilize in the sense those are actually based on this error rates. So let's look at what is this error rate. So suppose we want to estimate f from training observations x1, y1, xn, yn. So in this case, we are talking about supervised. Don't forget that. So today, whatever we are talking about, it is only supervised. So where yi's are qualitative, okay, meaning the class. So to quantify the accuracy of f cap is what is called training error rate. So we compute the proportion of mistakes that are made if we apply our estimate f cap to the training observations. Okay, so in linear regression, we check what is the difference between the predicted value and um, uh, the original value in the data set. So here also we are doing the same thing actually. We are doing an average of how many mistakes we have done. So where the class was A and we have said it's the other thing, right? So that can be written mathematically in this fashion. So 1 by n is average of mistakes actually. That's why error rate. So summation over I is equal to 1 to n, and here we use the term I. I is what is called an indicator variable. So this I basically means that yi is not equal to yi cap. Okay. So this is called an indicator variable. So that equals 1 if yi is not equal to yi. So that means predicted and the original class, if they're not same, then it contributes 1 to the summation. So the number of mismatch, you sum them, right? So it is basically the number of mismatch divided by the total number of observations. So the test error rates, so we look at what is my test error rates. So for the test data, we calculate this, right? This error rate. So error rates that results from applying the classifier to test observations that were not used in training. So test error rate associated with a set of test observations of the form x0, y0 is thus, we can say that it is average of this indicator variable y0 not equal to y0 cap. Essentially, I'm talking about this expression only. So it is the average number of mismatches, okay? Where y0 cap is the predicted class level that results from applying the classifier to the test observations with predictor x0. So obviously a good classifier is one for which the test error is the smallest. Okay, so this is the way we define it. Okay, so now we will just very quickly look at what base of this classification algorithms in general. Okay, so which is actually found from the statistical decision theory. Okay, so maybe we'll not go into much detail, but just to have a understanding of on basis of what this classification algorithms came up. So as we have seen, so it is a generalization. Okay, not like it can be applied to anything, whether it is classification or a like classification or a prediction problem. Okay. So you'll be looking at, so if you look at this title, statistical decision theory, quantitative, and the next one is what is called the qualitative output. So this qualitative output is your classification output. Okay, and quantitative could be even your prediction kind of things. Okay. So actually for quantitative output, we have seen with lots of examples that when we are really predicting some y, it is actually the mean of different y for the same x. If you have used different data set for modeling in order to get different equations of linear regression, right? If you remember that. So we studied that we were talking about expectation on the y. Okay, so given the same x, and if you use different data set for modeling your functions, then what is the mean value of y that you are getting? Okay, so that is what is a true prediction, and we have seen that that comes to the close to the true population value, right? So here also we'll be talking about expectations. So let's see. So if x is sorry, so if x belongs to, so x is the data set and predictor variables, and y is the response variables or the labels. So real valued random input and output vectors, and we assume that this x and y has a joint probability distribution, probability x comma y. Okay, so they have a joint probability distribution. So essentially what we try to do is determine the function y equal to f of x, minimizing the loss function. So for a linear regression, this loss function was nothing but this um, least square distance. Okay, so this loss function typically is represented like this: the loss function y and the f of x. Okay, the true thing and whatever your model has given f of x. And this, if you remember linear regression, you will see that it is basically the difference square, the least square, y minus f of x the whole square. So from here, actually, we can define what is the expected prediction error. So this expected prediction error of f, so expected prediction error of f can be written as expectation on y minus f of x square. And this can also be written like this: it is an integration of y minus f of x into probability of dx dr. Okay, so what we try to do is basically minimize this expected prediction error. We minimize the expected prediction error f cap x. Okay, so this is written in a very complex fashion, meaning that for which value of c we are getting this expectation. So we compute, find which, for which values of c we are getting the minimum expectation. Okay, so this is in general is what we try to do by modeling any uh, function that represent the data set. So the best prediction of y at any point x equal to x is what is called the conditional mean, when best is measured by the average squared error. So that is what I was talking about, this mean. Okay. So, and when the output is qualitative output, then again for that also we define a loss function. So we will not see much of it, but just understand this, that when the output is categorical, so let's say is a categorical variable g, so then we define this loss function as a matrix. Okay, so how this matrix L is defined? With a dimension k cross k. So k is basically the number of classes or categorical values. Okay, so that means it is a k cross k matrix. So if you have 4 classes in your data set, let's say, so then you will be having a 4 by 4 matrix. Okay, and what are the entries of this matrix? Entries of this loss function matrix. So any entry k comma l in that matrix is equal to 0 when k equal to L, so that is the diagonal. Otherwise, this L k comma L is basically is the cost of misclassifying class k as L. Okay, so that means k comma L, if k and L are not equal, it contains the cost of, if I have misclassified the class K as a L. Okay, so that is what is defined as. So now this cost you can define it in many ways. Okay, so each misclassification has a unit cost. We can make it that if there is a misclassification, let's say I am that contribute to a cost of 1. Okay, so simply if there is a misclassification, I'll be having a 1, otherwise I'll be having a 0. If it is classified correctly, then it is 0, otherwise it is 1. So that means this matrix is actually a 0, 1 matrix. Okay, so then for this also we can define an expected prediction error. So that is basically expectation of this matrix L, expectation of this loss G comma G cap X. Okay, so what it means basically is that the difference between the original G, so G is original and G cap is X is what is computed. Okay, and it is the loss, so this is the loss function. So what we try to do is basically we tries to again minimize this expected prediction error. Okay, so what essentially it means is that this expectation of L of G comma G cap X, so that can be written something like this, that expectation conditioned on X, summation K is equal to 1 to K over all the classes, the L Gk comma G cap X into probability Gk given X. So X is basically, don't forget that X is your predictor variables. Given this X, what is the probability that a particular entry will belong to a class Gk. Gk stands for a particular class. Okay, and given this loss function L Gk comma G dash X. Okay, so if you do I'm again leaving this mathematics. Simply what we can do, if you use this minimization, so if you have to minimize, then you have to do this differentiation and do all such things. So I'm not going into all these things now. So what essentially we can do is this G cap X. So simplifying, we can simply say that this G cap X, okay, means the predicted class is equal to a class K among all possible classes if the probability that given X equal to X, Gk, probability of the class being some K given X equal to X is maximum of probabilities of all the maximum of the probability of being in each class G given X equal to X. So I don't know if you have understood it. See, it means that when you do the minimization of this function, then what we get is that so this has a probability term over here. Okay, so what essentially it comes out to be, what result that you get from this is that you assign, given a particular input X, you assign that X to a class Gk if you see given X equal to X, I mean basically you see what is the probability of X being in class 1, X being in class 2, X being in class 3. So among all these things, whatever is the maximum probability, you assign the class of that particular entry X to this particular class Gk, wherever you have the maximum probability. Okay, so so this comes from a quite complex differentiation and equation, and then doing the matrix algebra, and then you actually ultimately get to this. So for classification problem, for any classification problem you talk about, it ultimately comes down to this probability. You check for every class, what is the probability of X being a part of that class, and then you choose the maximum probability. So with this basic, with these fundamentals, now we can move on to some classification algorithms. So in order for that, so the most, probably the first ever classification algorithm, that statistical classification algorithm that was developed was what is called this Bayes classification algorithm. So Bayes classification algorithm is a more general term. Typically, mostly what we use is what is called naive Bayes classifier algorithm. Okay, so let's look at this Bayes classifier a little bit. So I will talk about this Bayes classifier. I mean, I don't have the slides. I will start writing it. But let's look at some of the kind of properties of this Bayes classifier. So in Bayes classifier, we can prove that the test error rate is minimized on the average. So meaning that this expected prediction error is minimum in case of Bayes classifier. Okay. So what it essentially, so the algorithm is very simple in Bayes classifier. So it's a very simple classifier that assigns each observation to the most likely class given its predictor values. So this most likely class that comes from this fact, maximum probability given probability of a class G given X equal to X. So it comes from this fact. So that is what is the most likely class. So assign a test observation with a predictor vector x0 to the class J, for which this probability of y equal to j given x equal to x0 is the largest. So that is what we have seen in the earlier slide. Okay. So so for a two-class problem, we can think of Bayes classifier correspond to predicting class 1 if probability of y equal to 1 given x equal to x0 is greater than 0.5, and class 2 otherwise. So this is in case of a two-class problem. Okay. So so the points where the probability is exactly 50% is called what is called the Bayes decision boundaries. Okay, so about those particular entries, it's a little vague which side it will go, obviously. So Bayes classifier produces the lowest possible test error rate, which is called the Bayes error rate. Okay, so it is called the Bayes error rate. So theoretically, what it means is that you cannot do anything better than this Bayes error rate. So it is the theoretical lower bound on how good your classification can be. Okay, but there are some problems with this Bayes classification. So there are some certain things about this Bayes classification which actually you cannot measure or you cannot compute. That's why it is not really can be used in its true essence. Okay, so now we will go into this Bayes classifier in little more detail. So just before that, here is a simple example of what Bayes classifier can do. So it is a simulated data from the book that consists of 100 observations in each of the two groups. So there are two groups, one orange and one is blue. And this line, this dashed line, gives the Bayes decision boundary, where it is that probability is 50%, 50%. Okay. So this. So what you see is that in this Bayes classification, actually what is to be observed over here is that the boundary is not linear. That is one thing. Okay, And even though the data is very what to say, it's very congested and overlapping kind of thing, Bayes classifier could give a very nice boundary between the two different classes. And you see the error rates will be obviously, so misclassified data is very small, which is only along this boundary. So 1, 2, 3, 4, 5, 6. So very small number of misclassification on the orange side and very few misclassification on the blue sides. And possibly they can be thought of even as some kind of outliers also. That's why it has come up like this. Okay. So this is what Bayes classifier can do. So now let's look at, let's go into the details of this Bayes classification. Specifically, we will not actually do Bayes classifier because it is something like an impossible thing to do, minimize the errors. But because of the real time assumptions, but we will talk about the Naive Bayes classifier. Okay, so for that I don't have the slides, so I will use the notepad. Hello. Huh. So can you see this what notepad?
Yes, ma'am.
Writing. Okay. Okay. So as you can understand, it is based on this Bayes theorem. So you need to recollect what is Bayes theorem. So maybe we can re-look at this Bayes theorem once again in order to do the Bayes naive Bayes classifier. So what this Bayes theorem says, do you remember this? Probability of C given X equal to probability of X given C, probability of C divided by probability of X. So do you remember what is this? So this probability of C given X is what is called posteriori probability. Posteriori probability, which we really want to find. Okay, given up. So this C part, you can think of it as that particular class that we are finding out. Probability of what class? Given an X, right? And what is this probability of X? It is the, probability of C is the prior probability. Prior probability of this event C. P of C is the prior probability. And probability of C given X is what is called the posterior probability. Right. And this probability of X given C is what is called the likelihood. And what else I have? Yes. So this P of X is basically the marginal probabilities. So this P of X is actually the marginal probability. So if you cannot relate, let's start from the very basic. From the Bayes theorem itself, let's start. So suppose I have some elements like this. Okay. So let's say this is red, this is red, these things are red. Okay. And here also we have some red, here also we have some red things. Okay. And this is a green thing, this is also a green thing. Maybe here also I have a green thing. And then let's say I have some kind of uh, some shapes. Let's see. Okay, let's take some green triangles, again a green triangles, and let's say another red triangle. Okay. Now, okay, just one second.
Of taking a green shape.
Okay, now let's see. Okay, let me put this as red to understand properly. Okay. Yes. So if you have such a kind of things, we'll just look at Bayes theorem little detailed so that it becomes very clear. So if I want to find so if I want to find this probability of how many stars are there, then it is very clear that stars or triangles, let's say. I just draw that probability of these triangles. Probability of these triangles. So it may be, okay, I should not draw it in this color. So maybe I'll draw it with this. So what is the probability of this triangles? So how many triangles are there? So 3, this and this. So I'll be writing 3 by 10. So now if I want to see what is the probability of uh, green elements, so then what it will be? It will be green elements are 4. So 4 out of 10, right? So then conditional, given the event something has happened, then if you have to find that, then what will you do? So let's say if I want to find what is the, given that it is green, what is the probability that I'm getting a triangle? Okay. So if you have to compute that, then what it is going to be? So you will look at how many greens are there, right? So 4 greens are there, and out of that 2 are triangles, right? So this way you try to see. So now if you so this is what is probability that given green it is a triangle. The probability that it is a triangle given green is this much. So now let's see one thing. So if you try to write it in proper fashion, so this 2 by 4, what you are actually trying to do is uh, it is probability that this triangle intersection green divided by what is the probability of green. That is what you are trying to do. Okay. So similarly, you can also define the other way. Green and what this is triangle, right? So this can be again written as, so what it will be? It will be again probability of this triangle and this green intersection of this divided by, now it is the probability of the triangles, right? So now from here, what is common you can see is that this intersection part is common actually. So what we can write is that this probability that this triangle intersection green, this part is common, right? So this can be written as probability of green into probability of this triangle given green, or it can be also be written as probability of triangle into probability of this green given triangle, right? And if you notice properly, this is what is actually coming down to the Bayes theorem. So that means it is this, the meaning of this comes out to be probability of green into probability of triangle given green is equal to probability of triangle into probability of green given triangle. And now if you just rearrange them, then what it comes out to be, if you rearrange them, now it comes out to be what? That probability of triangle given green is equal to probability of green. I'm just writing it just by arranging little bit in the other direction. So probability of green given triangle into probability of triangle divided by probability of green. Okay. Now if you look at this Bayes theorem part that we have seen, you see probability of C given X, probability of X given C into probability of C divided by probability of X. So now it is of exactly of this form. So if I just, we can say this is C, this is X, right? And similarly, you can map over here. So green is X, X given C. So this is going to be C and this is going to be green is X. So that is what you are getting over here. See? Probability of C given X, probability of X given C. So maybe I can minimize it a little bit so that you can see this. So this delta, triangle is C, green is X. So you can just find the similarity with this. Probability of X given C, probability of C divided by probability of X. So this is what is that Bayes theorem, right? Now, how we'll be using it for classification? Let's see. So one more thing we need to see, what is this probability of green? Which is called the, which we said that it is the marginal probability, right? So this marginal probability, P of green is what? This P of green is nothing but probability of green given the triangle into probability of the triangle plus probability. Okay, I have to take the new page. Okay, let me write it once again. So probability of green equal to probability of green plus triangle, sorry, not plus, given the triangle into probability of triangle plus probability of green but not the triangle into probability of not the triangle. Okay, so probability of green is together is going to be like this, right? Probability of green given the triangle into probability of triangle plus probability of green given the given not the triangle and probability of not the triangle. So now we can generalize that probability of A given B, and you also have seen the Bayesian formula, Bayesian theorem in this format. So it becomes probability of B given A into probability of A divided by, basically I'm writing it once again with this P green in expanded form of this. Okay. So probability of B given A, probability of A divided by probability of B given A into P of A plus probability of B not A into probability of not A. Okay. So now this again can be generalized for multiple events. So how will it look like? Let's look at that. So the generalization also we have seen when we did this probability things. So probability of, let's say, A given x1, x2, x3, certain events that has happened. Okay, let's say there are just three things. So then probability of x1, x2, x3 given A into probability of A divided by probability of x1, x2, x3 together, right? So now again, this can be written using this Bayes theorem. How? It can be written as probability of x1 given A into probability of, so this is what is important, probability of x2 given x1 has happened and A has happened, right? Then probability of x3 given x1, x2 has happened and A has happened into probability of it. So I'm expanding this part and divided by, this part is similar to the previous one. So probability of x1, x2, x3. Okay. So now comes the what is called naive Bayes. So now you see here we are considering the influence of x1 and the A. Here we are considering the influence of x1, x2, A. So over here we are considering the influences of all, like x1A, then x1, x2 and A and so on, right? Then initially we have taken x1, then x1A, then x1, x2A. So all the things we have taken, right? So, but how will you get this influence? Question is how to compute these influences. So it comes from what is called the joint probability. Okay, and this is unknown to us. Okay. Okay. So that's why what we assume is that in naive Bayes classifier, what we assume is that the events are independent. So we assume events are independent. So if you assume that events are independent, then how that expression changes? Let me just. So then the expression then becomes P of A given x1, x2, x3. So the new naive Bayes looks like this. It's equal to probability of x1 given A, probability of x2 given A, probability of x3 given A into probability of A divided by the probability of x1, x2, x3. So what we are seeing is that all these are independent. So we are removing we are assuming like the influences of the previous things are not there. Okay. So this is so once you are having this formula, so this is what is called this naive Bayes formula. So once you have this, then you find the probabilities for a given x, okay, and whichever class probabilities for a given x for all classes, okay, so for all classes, and then whichever class has the highest probability that gives you the predicted class. Okay. So have you done the naive Bayes classifier earlier?
Yes, ma'am, in third sem.
Huh? You
Yes,
have done?
yes, ma'am, third sem.
Okay. So do I have to do an example then? Or should I leave? I'll be using that typical example. Which example you did for Bayes classification? What you have studied in naive Bayes classification? You have just studied the algorithm or what?
Yes, ma'am, we used a bias computer data set to predict whether given a specific, say, user, whether the user will buy the computer or not buy. So using a binary class variable, we've done the
Binary class variable, you have done that.
Yeah,
Okay.
yes, ma'am.
So should I do this once again then, or I can leave it over here? Tell me. Then I'll move on to the next. What? Yes, no, something you must say.
Small example would be good, ma'am. Then
Small example would be good.
yes, ma'am.
Okay. So this is the typical example of, maybe you have seen this example many times. So you have those day number, this outlook, humidity. So these are the parameters, the attributes, sorry. Whether it is windy or not, and then you have whether you should go for playing or not. Okay. So there are 8 days of data, 4, 5, 6, 7, and 8. So these outlooks are defined to be like sunny. So this is also sunny. Then this is overcasted. Then raining. Again raining. Again here overcasted, sunny, and raining. Similarly, humidity, we have highly humid, then or heavy. So let me write it as heavy. High or high. So this is high, this is normal, this is again high, then normal, normal, this is low, high, and low. Windy is just a true false kind of thing. So let's say false, 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 true, 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 true. And display, let's let it to be y, y, y. Yes, 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 no, yes, no, yes. Oh, sorry, initially I made a mistake. So let's say this is no, yes, 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 no, yes, no, yes. Okay. So now how do you predict using this Bayes classification? So let's say my input X is something like that, that it is, if it is rainy and then high humid, okay, and not windy, and windy is false, then predict whether you should go for play or not. Play is yes or no, what is it? So for this, what you need to do essentially is that you have to predict. So here you apply your naive Bayes. So that means if I look over here, so predict display given all these three parameters. Okay, again here like x1, x2, x3 is what? Rainy, then what? Humid, high humid, and false. Windy is false. So this is what you need to predict. Okay. So this play equal to yes, and also you have to compute whether play is equal to no. For both the things, you have to do the same thing, and then whichever has got the higher probability, we will take that as our predicted class. Okay. So that means what we need to predict play equal to yes given all these parameters R, H, W, R, H, F. R, H, F meaning this rainy, high, and windy equal to false, and also you need to give whether play equal to no. Given RHF, what is the probability of play equal to no? So can you find these values by looking at it? So what all things you have to find? So for this, you actually have to find all this probability of x1 given A, probability of x2 given A, and so on. Okay. So you have to find probability of yes, you have to find probability of no, right? What is the probability of yes over here? So 1, 2, 3, 4, 5. So probability of yes is going to be 10. So this is going to be 5 out of 8. And what is probability of no? So 1, 2. So 2. Now, 1, 2, 3. Sorry, 3. 3 out of 8. Take a new page again. To need this information. So this is 3 by 8. I'll write it like this so that I can see. So then what probability that rain, right? Rain and given it is yes. And we also need to find probability of rain given no. That's for the other part. Both the things we have to find, right? Play yes and I mean both the things we need to find. That's why we are calculating at the same time. So probability that play is yes. What's the probability of rain given playing is yes? So what it will come out to be? Out of 5 yeses, yes, rainy is how many? How many is rainy? 2. So 2 out of 5. And no, that means remaining. Sorry, out of no, how many were no? 3 were no, right? Yes. Out of 3 no playing, how many?
1.
It's 1, right?
This is the 5th day.
Okay. So 1. So like this, can you now complete? This way we can, okay, maybe for 1 we will do. Then probability of, then next what we have to see? High, yes, and probability of high, no. What it comes out to be, let me just tell you this. Out of yes, yes is always 5. Let me just write it down. How many yes is high? How many yes is high? This is 1 high, I can see. Is it 1 only?
Yes, ma'am, just 1.
1. Then for no, playing to be no, how many is yes? Sorry, how many is high? 1, 2. So 2 out of 3. Right? So this way you can keep on calculating. So the last one remaining is what? False, right? False, and you have to say what is yes, false, and no. So how much it is?
3 out of 5.
3 out of 5, and here no and false. So no and false, 1.
Yes, ma'am.
1 out of 3.
Yes, ma'am.
Okay. So done. Now with this I have to now compute the values, right?
Yes, ma'am.
So then probability of play equal to yes given RHF. So this comes out to be, I have to consider all these yes parts, isn't it? So probability of yes, below it is going to be 5 by 8, right? and above what we are going to have all these multiplications according to this formula. So probability of this x1, x2, x3, right? So this is that I have written, and this is x1 given a, x2 given a, and then probability of happening of this a. So this comes out to be what? Oh, not 5 by 8 will not be over here, sorry. Probability of A is what? This one will go up, probability of it. What it was, 5 by 8. It will be 5 by 8 over here. And here what all things will get multiplied? All this. So means 2 by 5, 1 by 5, 3 by 5, right?
Yes, ma'am.
And it is divided by what it will be? It will be divided by what? This probability of x1, x2, x3. So now notice one thing, okay? The thing is that, yes, so this is what I wanted to say. I forgot that to say. The thing is that this part actually you don't have to really compute. Why, you know? Because when you do, okay, let me just take another page. New page. After this, no, after this, no. New page at end. Okay. So let me just tell you one more thing. You really don't have to compute the below part. Why, you know? Because when you compute for this no part, okay, probability of what is it? Play equal to no given x1, x2, x3. Okay, I will not write x1, x2, x3. What I should write is what? Rainy, high, and false. So I have to calculate this part also. So here also what we'll find is below that x1, x2, x3. Isn't it? So that means this part is going to remain common. So this part is remaining common for play equal to yes, given that conditions rain, H and F, and play equal to no, given RHF. Right. So that is why it doesn't make really computing it. So simply what we can do is after this, I will compare among them this play equal to no and RHF, what this value comes out to be. So in this case, what it is, here it is 3 by 8, no part, and all this no part I have to combine. So that means what all things? 1/3, 2/3, and again 1/3, right?
Yes, ma'am.
So this becomes what? This 5 gets cancelled. 2, 4. So the first one becomes 3 divided by 100, and this comes out to be 2 divided by 4. So it is 1 divided by 36, right? So which one is greater? Tell me. Which one is greater?
The above
Tell
one
me.
is 0.03. And
So this is 0.03 and this is
0.027 recurring. Yes.
okay. Right, 0. So which one is greater?
The yes, uh, the yes one is greater.
Yes, part is greater. So that means the class probability is going to be this one. Okay. So that means given this RHF, this we are going to get this maximum probability that we saw is over here. So that means this is going to be the predicted class. Okay. So now what is the problem with this way of doing classification? That is, and how that can be taken care of, that is one thing. So notice over here one thing. In this part, all these parts, okay, if anything does not have a count, for example, this one, there is nothing which is yes in this category of what it was, unit. So if there is nothing high over here, so that means what it will become, this component is going to be 0, right? Are you able to see what I'm trying to say? So
Yes.
if one of the count becomes 0, so then since it is multiplication of all these factors, so the entire thing comes out to be 0. So that means you are unable to classify properly then. Okay. So that is why sometimes people does some kind of, in order to get a positive value. So what people does is what is called smoothing. So in case a particular what should I say, a particular probability of how do I say, a given x is 0, we apply what is called a Laplacian smoothing. Laplacian smoothing technique. Okay. Now using this smoothing technique, what happens? So you try to make that nothing becomes 0. So what is the easiest way of doing that so that it does not becomes 0? So what it does is it rewrites the probability that a particular, let's say, feature or attribute is equal to a particular, taking some particular value, given that x is equal to, it is given like this, it is the number of that feature equal to v given x plus 1. So that means if there is no class with there is no value with equal to v, so I'm adding a plus 1. So if it becomes 0, then definitely it will be added by this 1 and you will get some value on the denominator. And that is why below what you do is this ny plus divided by the size of the total number of possible categories in this feature. Okay, so ny is what? Ny is total, ny is the total number of that yes or no, as we were doing it, right? Yes or no, or total number of that way, yes, total number of yes or no in this case, in this particular example. And this v feature, so the cardinality of v feature, it is nothing but the total number of possible categories. meaning in this case high, normal, and low, high, normal, low, etc. So if there are 3 categories, then it is going to be that 3. So this is how you can avoid something becoming 0 and giving a wrong interpretation of this classification problem. Okay, so this is about the Bayesian classifier. I will just I will keep this thing saved and give it to you in case I'm not able to modify this slide. Now let's go back to this slide once again. So with this naive Bayes classifier, what it is expected is that it will give a very given the assumption that all these variables are independent, no one influences the other, it is going to give a good result, good classification score, good less error rates, and but it will definitely not give the least possible. The least possible you can get only by that Bayes classifier, where all the interactions are known beforehand and you can use that Bayes theorem in its true sense. Okay, so the next what we will look at is this one of the approximation kind of algorithm which performs pretty well in the classification domain. So this is what is this k nearest neighbor. So all of you know the k nearest neighbor algorithm, I'm presuming. So let's look at a little bit of this background. So theoretically, that's what I was saying. Theoretically, we'd always like to predict qualitative responses using the Bayes classifier. Okay, but we do not know the conditional distribution of y given x, right? So that means that influences I was talking about, and thus it only serves as an unattainable gold standard against which to compare other methods. Okay. So, so KNN, now if you look at it, so we need other methods. So given a positive integer k and a test observation x0, so the KNN classifier first identifies the k points in the training data that are closest to x0. And this is represented.
Not visible, ma'am.
Oh, acha, I'm not স্লাইডটা দেখাটা ভুলে গেছি। হ্যাঁ, এবার দেখা যাচ্ছে?
Yes, ma'am.
Yes. Okay. So this KNN, so the KNN given a positive integer k under test observation x0. So the KNN classifier first identifies the k points in the training data that are closest to the given point x0. And this k points actually represents the neighborhood, which is identified by this notation capital N0. Okay. So then what it actually does is it estimates the conditional probability for class J as the fraction of points in N0 whose response value equals J. So that is what, when you do this algorithm of k nearest, so mathematically that particular thing, you can express it in this fashion. So it estimates so everything is an estimation. So this probability you are estimating the conditional probability for class J. So this is what probability that y equal to class J given x equal to x0. So that you are saying it is the fraction of points in N0 whose response value equals j. So that's why it is 1 by k summation of, see, I is again an indicator variable, meaning that the level of yi is j for all those neighbors. Okay, so for all those neighbors where level is j, that those are summed and divided by k. So it is a kind of, I'm doing an average. So this is a general kind of rule, so which you can even apply for doing a regression also, for prediction purposes, even though it is not a class. So you can predict real values also using this method. So that's why there is a averaging of that. But typically for classification, what we say, we take the majority vote. So whichever class has the highest number of count in the neighborhood, the point X gets that point. Okay, so this is a generalization that we are talking about. So that means finally KNN applies Bayes rule and classifies the test observation X0, that the class with the largest probability. So you can see that how it is relating to that main concept of probability. So while computation, we really don't do it as a separate thing, but actually you can do in this fashion also, that you find out the averages for all possible j's, and then whichever has the highest probability, that one you take. So theoretically, that is what is KNN algorithm, for which we can define it. I mean, this way we can define the k nearest neighbor problem in the framework of that computation of the probabilities. So what are the properties of this k nearest neighbor? So it's non-parametric algorithm, supervised. Non-parametric in the sense that we don't estimate any parameters over here, like linear regression, beta 0, beta 1 and all that. It is supervised, obviously. You can use KNN for multiple class classification. So as I said, so logistic regression is also a parametric algorithm where we need to estimate different parameters like linear regression. So k is basically the number of neighbors of a given point X to be chosen around, and k is, in this case, is a kind of tuning parameter, and this k is kind of independent of the data. Okay, I mean, not in, I should not say independent, but I can say that it is not derived from the data. Okay, so this KNN is called lazy learning because actually you don't build a model in the beginning like logistic linear regression. So where we actually build the function and then for any from the data, and then whenever a new data comes in, we fit it into the equation. So here in this case, what we do, we don't have a model as such. Whenever a new data comes, we simply use this KNN heuristic algorithm to predict the class of it. Okay, so that's why it is called a lazy learning. So since computation has a deferred alternate classification, and there is no explicit training kind of phase. So there is no training phase over here, no generalization as such. So the function is approximated locally, unlike logistic regression. So since we are talking about k neighbors, so we are restricting ourselves to a very small view near the given point X. So KNN is typically used when decision boundaries are non-linear, when it is very difficult to separate different types of classes and there are large volumes of data. So inputs can be quantitative or qualitative. Output is categorical value, the class. So if it is a qualitative thing, then you have to appropriately scale to the standardize or scale to the rest of the data set, so that the qualitative data is not kind of out of range of the remaining set of attributes. So KNN could also be used for function approximation problem, means that prediction or regression problem, linear regression problem, by averaging the y values of the k neighbors. Whereas for classification, it uses the majority voting of k neighbors of inputs X. So here another thing is that we don't assume any kind of data distribution, or we don't assume that the classes are linearly separable. That means there are cleaner, distinct linear line which separates different classes. So this is because it is non-parametric. So what we need to do is we need to find the best k value. So what is the number of neighborhood points you are going to consider by running the KNN algorithm for increasing number of k values. So there is a kind of trial and error method to decide the value of this k. So that is what is tuning. So we need to tune. So the algorithm is very simple. So how do you define the k neighbors? So we define the k neighbors of a given point x using different distance. Sorry, this should be distance. Using different distance metric. So we find the distance between x and the points in the data set. So it should be in the data set. So what kind of distance metric? Euclidean distance, Mahalanobis distance, Hamming distance, depending on what is the situation. Then there are many other several types of distances. Manhattan distances also you can use. So several possible distances are possible. So in the algorithm, so we compute chosen distance metric between the test data x and all labeled data points. So it takes big O of n times d because d is the total number of features. So even if you use Euclidean distance, so finding out the difference of all the d things, okay, and then squaring them, adding them, then taking the square root. So that is how you will be calculating your distance metric even if you use Euclidean distance. So that is why d also will be considered over here. So it is, this part is going to take this big O of nd time. So after that we select the closest k labeled data points of x. So this closest, choosing this close, for this actually you don't need to do a sorting or anything. So if you do a sorting, it is going to be that n log n time. So what you can actually do is that k times, if you have decided on that k is your 3 or 4 or 5, something like that. So 5 times you run, find what is the minimum number excluding the previously found things. So that's why we say that this can be done in big O of n times k. Okay. So, and then we find the class level that the majority of the k neighbors have and assign that label to x. Actually, this particular thing you can do at the same time over here. You can count for each class how many counts are coming. So that is also no more than this big O of k time. So overall, we can say this time complexity is nothing but big O of nd plus k times n, because this k because of this big O of n times k. Okay. So this is the algorithm that you have learned, probably implemented also many places. So now there are certain issues that we can think about, like what are the merits, demerits of this k nearest neighbor algorithm, and what are the issues that you need to think about. So the best choice of k depends on the data. So you have to do a kind of trial and error. So for large k values, typically if you are taking k value to be greater than 20, so then it reduces the effect of noise on classification. So noise in this sense, it can be outliers. Okay. So, and as a result, what might happen is that it might underfit. It may not fit in properly. So that means what in this case, so underfitting would always mean that there is a high bias and low variance. And we have studied that earlier, that bias and variance, they are kind of contradictory, okay, most of the time. So high bias and low variance, but robust to outliers. Okay. So may overlook, so because of this high k value, so you can understand that you are looking for the class of a point X which has a very large neighborhood. So if you are increasing the distance from that point, obviously they will be less similar to those further points, right? So that's what is written over here, that it may overlook the local patterns. So it will put more emphasis on how far those data, the farthest point also, in order to decide the class. So it is good for large data set with many outliers because it is more robust to outliers. So if you take smaller k values, for example, k is equal to 1 or k equal to 3, then the problem is it will be affected by the noise. So this causes overfitting. So, but what it actually means is that it produces complex flexible boundaries. So the boundaries will be very minute kind of thing. So as a result, we will be having lower bias, okay, but high variance. High variance will mean overfitting. Okay, so we'll be using smaller k values for data sets where we know that there are the patterns are very local. I mean, from the very small neighborhood, we'll be able to identify its class. Okay, so when data are already kind of clustered in one places whose influence is not far off, then possibly if you know those information about the data, probably then we can choose. So typically this k equal to 5 to 10 is sort of gives a balance, and usually we take k to be odd so that we don't have to resolve the ties when you are doing the majority voting. And this performs well when you remove the irrelevant and redundant features. That means that dimensionality reduction and feature extraction kind of things are required, very much required for k nearest neighbor to give good results. So if you now look at the merits, then obviously it is very simple and intuitive, easy to understand and implement. No training phase, that we have already talked. Lazy learner. Non-parametric, so no assumptions are made about the data distribution, and that's why it is good for non-linear data. It is versatile, can be used for both classification and regression tasks. And demerits is that obviously it has the computation cost is little high, not high as high compared to the other classification algorithm, but you can consider it is high because every time it has to calculate the distance between a new point and all training points. So if you have large data sets, then it may become little slow. Memory intensive because always you have to keep the entire training data set to make the prediction. Another point is that curse of dimensionality, which I was talking about. So performance degrades significantly as the number of features increases, because the distance metric becomes less meaningful. So that's why you need to have this dimensionality reduction. So redundant, irrelevant features you must remove, and you must do dimensionality reduction. Sensitive to noise and outliers, that we have seen. Noisy data can skew the result, because we have it is seen that KNN will perform good on if your name if the pattern is most visible locally rather than from far off distances. And it requires feature scaling that I was talking about. So different attributes are in the different range of values, so they need to be standardized to a one scale so that no particular feature overpowers or dominates over the other features. So this feature scaling is also important thing. So you use KNN when the data set is small and noisy, and when you need to have a quick interpretable solution, and when data does not conform to any linear assumptions. Okay, so for k nearest neighbor, I did not give any example. Um, you have done already possibly. So I'll give you some assignments to see this naive Bayes classifier k nearest neighbor for the same data, how it performs. In fact, I have given you one assignment on this linear regression and asked you to do the analysis of the data. So similarly, I'll give you again another exercise which you can perform on your Python using, maybe you can use in the library, or you can write your own k nearest neighbor experimenting with different k's and see how they evaluate. So now how do you choose a particular k? So typically these two methods are used, what is called this elbow method and k-fold cross validation. So let's first look at this elbow method. So in elbow method, so I will update these slides some more. So with little bit of diagram, or maybe you can do a Google search also in order to find this. So in elbow method, what you do is you simply draw a graph showing the error rate or accuracy for different k values. So you will have x-axis and y-axis. X-axis you will be having different values of k. On the y-axis you can have the mean square error rate. So it is the number of mismatches for different class and the average of it. Okay, so that is what is the error rate, how it is defined, right? So we talked about error rate. Or even you can do this confusion matrix also in order to look at the accuracy. So you can take the accuracy parameters also doing the confusion matrix. So for different k values, you look at that. So you will see as k increases, the error usually drops in the beginning. But after a certain point, error stops decreasing quickly and then it becomes like steady. So that is why it is called elbow. It looks like an elbow. First, from the shoulder, if you just look at your hand, from the shoulder to the elbow, it decreases, and then after that, it becomes more or less horizontal to the x-axis. So that meaning that there is, even if you increase the neighborhood number of points, the result significantly does not improve. Okay, so this way we choose a particular k. I mean that elbow, at the elbow point is the optimal k that we decide. The point where the curve changes direction and looks like an elbow is usually the best choice for k. So this is one way of deciding what is the best k for a given data set. Obviously it is a little expensive because for each k value you have to run the KNN algorithm. So there is another one which is called k-fold cross validation. So given time, we'll see a little more about this cross validation. So in k-fold cross validation, what you do is typically we divide the data set into k parts, and then this model is trained on some of these parts and test on the remaining ones, meaning that, so for with respect to KNN, how it is done, we will see little in the next class. So here what we see is the k value that gives the highest average accuracy during this test is usually the best one to use. So we'll look at this k-fold cross validation in the next class in little more detail. Both the methods we will look at it in the next class in little more detail with figures and pictures. With this, the KNN thing is over. So here actually I've just given some examples showing this Bayesian thing and KNN, and I will ask also you to do this experimentation using your Python, and using the data set that you already have visualized, or maybe you can take different data set also. So I would prefer that you do it on the data set that you have done the visualization. So if it is a classification kind of problem, if your data set that you have chosen there you cannot find a classification problem, then probably you have to choose a different data set and look at these things. Okay, so here let's look at an example. So about this KNN approach. So this diagram on the left hand side. So here, so the k value is taken to be 3. That means for a particular given point x, unknown point, we are looking at 3 neighbors using some metric. So in this case, these are the 3 points along with which are the neighbor of this x. I mean, these are the 3 nearest values of x. Okay. So, and there are 2 classes you can see, orange and blue. So now if you look at this figures, so this black things is what is giving the k decision boundaries for the KNN. Okay. So so what you see is that this decision boundaries is neither continuous nor it is linear. So it is very flexible. Okay. So that means all these points within this decision boundaries will belong to the class blue. All these blue points over here on the right hand side also will belong to the class blue, and rest of the things over here is going to be in class this orange class actually. Okay. So the important thing to note is that as we are talking about that k nearest neighborhood does not produce a linear boundary, and so the data for which we know that there is no clear linear separation between between different classes, we can safely apply our KNN approach. So this diagram actually shows that. Okay. So now let's look at this KNN and Bayesian decision boundary for k equal to 10. So surprisingly, you will see that for a value k equal to 10, so which is not very big, this k is not very big, not very small. So k less than equal to 3 is considered to be small, and k greater than 20 is supposed to be very big. So k equal to 10 is somewhat like a nice value. Okay, I forgot to say, oh no, yes. Okay, yes. So k equal to 10 is not a very bad value. So you see over here, this dashed line is the Bayesian boundary, and KNN is the boundary is this black solid line. Okay, dashed line is Bayesian and this solid line is KNN boundaries. So what you will see is that they are not very far from each other. Okay. So what it suggests is that for a k value, a kind of balanced k value, k equal to 10. See, what we said is that Bayesian thing is something which is kind of a gold standard or ideal. So what we see is that for a moderate k value, the performance that it gives is a kind of standard or normal. I mean, what it is possible to achieve. Okay, so this diagram shows that. And you will see that this misclassifications are very small when you use a testing data and a trained data kind of setup. Okay. So here there is an example of when k is equal to 1 and k is equal to 100 for a k nearest neighbor. So left hand side k is equal to 1, then what kind of decision boundary you are getting, and when k is equal to 100, then what is the kind of decision boundary you are getting. So in both cases you see that Bayesian decision boundary is going to be the same. Okay. So if k is equal to 1, you see the decision boundary to be very, very flexible, right? It's very, very flexible, and that's why we say that it is a low bias but high variance. So it is overfitting kind of thing. Okay. Now, as K grows, it becomes less flexible and produces a decision bound that is close to linear. So the right hand side figure. See, it is almost like it is becoming a linear kind of thing. So which represents high bias, that means underfitting, and low variance classifier, and the low variance classifier. So if you compute the test error rates the way we have defined 1 by n into summation of mismatch. Okay. So then in the first case it is 0.1695 and in the second case it is 0.1925. Obviously for 100 it is the errors are more. Okay. So that suggests bad prediction. Okay. So now if we look at KNN training and test error rate, so this is typically like if you, I mean, for KNN you don't, I mean, if you given data set, if you separate a part of it for training and part of it for testing, in the sense that you don't include the points, the test points you don't include in the beginning, and then try to fit those new values and put it test values and see, look at the neighbors and then try to compare with the original levels of the test error data set. So that is the situation we are talking about. So in this case we are dividing the data set into training and testing, and then we are performing the training and test error rates. So this kind of graph we have also seen for linear regression. So what we see is that, so this is the diagram. You see on the x-axis what we have is 1 upon k. Okay, we have made it 1 upon k. Okay, so as you increase the values of k, 1 upon k becomes smaller and smaller. Okay. And on the y-axis, we have the error rate, meaning the average number of mismatch. Average number of mismatch. Error rate is nothing but average rate of mismatch. So what we see is that there is no strong relationship between the and okay, yes, one more thing. This blue line is training errors, and the orange line is the test errors. Okay. So what we see is that there is no strong relationship between the training error rate and the test error rate. So they are going like on their own. So when k is equal to 1, that means there are lots of flexibility. We have seen that decision boundary is very, very flexible, right? So that time obviously KNN training error rate is like almost 0. Okay, training error rate over here. It is almost like a 0. Okay. But test error rate may be quite high. KNN test and training errors, so here that I have said already plotted as function of 1 upon k. As 1 upon k increases, the method becomes more flexible, right? That is what we have seen. As 1 by k increases, the method becomes more flexible. So just to compare with regression, so just like regression, the training error rate consistently declines as the flexibility increases. That will always happen, be it regression or this classification. However, the test error exhibits a characteristic U-shape. So this thing, initially it was becoming small, and then again it is increasing. So that is the typical nature. Even in linear regression, we saw this kind of thing. So declining at first, and when k is somewhere near 10, so this is 0.10. So when k is somewhere near 10, then that is a kind of balance. Then again it started increasing. And it became, I mean, so then it was like a overfitting of things. Okay, so this is all I think I have. Yes. So this is all I have about this. classification today. So what in summary, what we saw is that we saw, other than that confusion matrix, we'll see confusion matrix also. Other than this confusion matrix, there is a way to assess the accuracy of the classification models using average number of mismatch of classes. On the basis of that, a model that can be thought of is the naive Bayes classifier. The Bayes classifier, if you know all the interactions, the joint probabilities of all possible features that are included in the model, then naive Bayes is going to, the Bayes classifier is going to give you the minimum error rate. Okay, the errors that cannot be removed at all. I mean, so you can reach that, but unfortunately, we don't know the joint probabilities of different features that are interacting. So that's why we have the naive Bayes classifier, where we assume that the attributes are all independent, and with that assumption, given a data set, we can find probabilities of a particular event, okay, being in a particular class. So we have to find the probabilities of that event giving a class. For each class, we have to find the probabilities, and among them, wherever we get the highest probability, that is going to decide the class of that particular entry or that particular test point. So this is about naive Bayes, and then we saw which is based on the Bayes theorem, in fact. And so it's a simple classification algorithm. Second, we saw k nearest neighbor. That is also a very simple classification algorithm, but again based on this probability measure, we actually find the highest probability, the probability of x taking a particular class, of all the classes we compute and choose the highest one. But in order to do the computation easier, we use that majority voting principle. So which is essentially doing the probability calculation, because we check how many classes, how many entries are belonging to a particular class compared to the rest of the others. So here we saw the how KNN is also actually a probability based method of classification, and then ultimately we saw that for how to choose this KNN, the K value for a KNN, and we talked about what could be a good value of K, and then we also saw that this training and test error rate for KNN, how it varies depending on the how you take the values of K. And we saw that if you take the value K between some 5 to 10, then it gives more or less a good result. And you have to actually do this trial and error in order to see the error rates with respect to the choice of the number of points in the neighborhood. Okay, so this is all. So next we will move on to this logistic regression in the next class. Okay, then, so give me the attendance. Okay. Hello.
Yes, ma'am.
Hello. So send me the attendance also, and that's it. Happy voting. So anything else you would like to say?
No, ma'am, it's good.
Okay. Okay, then I'm leaving. Just give me the attendance. Send me the attendance letter.
Thank you, ma'am.